Welcome to the Explainer. So glad you could join us today. Look, if you've ever stared at a dense, jargon-packed machine learning cheat sheet and thought, where do I even start? You are definitely in the right place. Today, we're taking all that overwhelming info and transforming it into a clean, easy-to-understand visual map. All right, let's just dive right in. Here's our roadmap for the Explainer. We'll quickly touch on what ML actually is, explore its three main categories, and then get into predicting, classifying, and finding hidden patterns. Think of this as your personal taxonomy tour to finally structure this complex world. Section 1. What is machine learning? Before we get lost in the weeds with specific models, let's just quickly ground ourselves. Simply put, machine learning, or ML, is a subset of artificial intelligence. Its whole job, enabling systems to learn from data, spot patterns, and make decisions. The really crucial takeaway here is that it does all this with minimal human intervention. We aren't hard-coding rigid rules anymore. We're literally just letting the machine figure the rules out from the data itself. It's a total game changer. So why should we care right now? Well, ML dramatically boosts both accuracy and efficiency, and because it learns from data, it actually gets better over time. The more high-quality data you feed it, the smarter it gets. This means smarter decision-making across the board, powering those real-world applications we rely on every single day, from your streaming recommendations to cutting-edge medical diagnostics. I love this visual because it perfectly captures the intersection of human-like logic and raw data. On one side, you have the biological brain representing our pattern recognition, and on the other, the digital circuitry. Bridging that gap are coding languages like Python and R. They're the essential tools we use to wire our human logic right into the analytical brain of the machine. All right, moving on to Section 2, the three categories of ML. I like to call this the Great Divide. So the entire ML universe basically splits into three distinct branches. First up, supervised learning. This is where you train your model using labeled data. You pair the input with the correct output so the machine learns the mapping. Easy enough, right? Then we have unsupervised learning. Here the data is totally unlabeled. The model acts like a detective, digging around to find hidden structures all on its own. And finally, reinforcement learning. This is where an agent learns by interacting with an environment, racking up rewards or penalties to figure out the best possible strategy over time. With that framework laid out, let's step into Section 3, predicting and classifying data. We're going to zoom in on those supervised workhorses. Our very first stop, linear regression. This algorithm predicts a continuous value by fitting a straight line between an input, x, and an output, y. The primary goal here is super straightforward. Just find the best possible line that minimizes the error between its predictions and the actual observed data points. Take a look at how this best fit line slices right through the data points. The algorithm is basically calculating the vertical distance, which is the error, between each point and the line, and doing everything it can to shrink that down. In the real world, this is absolutely perfect for business analytics. Think predicting future sales based on ad spend, or forecasting house prices based on square footage. Now, let's flip the script a bit with logistic regression. While linear regression predicts a continuous sliding scale number, logistic regression is actually a classification algorithm. We use it to predict the probability of a categorical outcome. We're talking strictly binary, black and white categories here, 0 or 1, yes or no. So instead of a straight line, this model uses what's called a sigmoid function. It squashes the output into a neat little probability between 0 and 1. If it's 0.5 or higher, boom, it belongs to class 1. If it's lower, class 0. This exact mechanic is running behind the scenes all the time. It's how your inbox decides if an email is spam, or how businesses predict if a customer is going to cancel their subscription. Moving on to something a little more heavy-duty, the support vector machine, or SVM. The goal here is to find the optimal hyperplane that maximizes the margin between different classes. I know, hyperplane sounds totally sci-fi, but honestly, it just means a boundary. It's an absolute powerhouse for high-dimensional spaces where drawing a simple straight line just won't cut it. Check out how the algorithm essentially transforms the data into this n-dimensional space to find that perfect boundary. It's trying to maximize the margin between our two classes, the blue dots and the purple dots. And the wider that margin, the better the model will perform on brand new, unseen data. This makes SVMs the go-to for really complex tasks, like image classification or even sorting through massive text databases. All right, let's shift gears to Section 4, the power of ensembles. We've looked at lone wolf models, but what happens when we team them up? To really grasp ensembles, let's compare a single decision tree to a random forest. A single tree is great, but it's famously prone to overfitting, meaning it gets way too obsessed with the specific quirks of its training data and totally chokes on new info. An ensemble method, like a random forest, fixes this by taking a majority vote from dozens or hundreds of trees. The big takeaway here? By combining a bunch of weaker models, you create one incredibly stable, highly accurate supermodel. Here's how it actually comes together. The algorithm creates multiple bootstrap samples from your dataset. Then it trains a unique decision tree on each of those samples. When you need a prediction, every single tree makes its own guess. The algorithm tallies them all up, takes the majority vote, and that's your final answer. It handles massive datasets like a champ and pretty much neutralizes that nasty overfitting problem we just talked about. Okay, stepping over to the unsupervised side now. Section 5, Finding Patterns with Clustering. Time for that detective work. A classic example of this is k-means clustering. It follows this really elegant 4-step iterative process. First, it drops k number of initial centroids onto the map. Second, every single data point snaps to its nearest centroid. Third, the algorithm calculates the mean of those points and updates the centroid to that new center. And fourth, it just repeats that whole dance until everything stabilizes and the points stop changing teams. If you follow this visual from left to right, you can clearly see how those randomly dropped centroids eventually pull the raw data into distinct, color-coded clusters. The ultimate goal is simply finding and grouping similar data points. This logic is absolutely crucial in the real world. Companies use it every day for customer segmentation or for anomaly detection to flag weird outliers that just don't belong in any normal group. We have covered a ton of ground today. Let's wrap things up with Section 6, Essential Key Takeaways. If you want to truly level up as an ML practitioner, definitely keep these takeaways in your back pocket. First off, really understand the algorithms. Know exactly when and why to deploy each one. Second, use the code as a starting point, but don't be afraid to tinker and customize. Third, always work with real-world data sets. Fourth, focus on tuning to squeeze out that extra performance. And finally, build, learn, and repeat. Consistency is literally the only way to master this stuff. I love this simple, bold directive right here. Keep learning, keep building. I highly recommend you save these concepts, revisit them often, and just practice. Get your hands dirty. Play around with those code snippets on real data sets. That deep intuition for how these models actually tick, you only get that by building. I want to leave you with this amazing quote from our source material. The best way to predict the future is to invent it. You've now got the visual map to the exact algorithms shaping tomorrow's tech. So here's my question to you. What will you build first? Thanks so much for hanging out with me on The Explainer today, and hey, keep exploring.